Hello there, welcome back. Chapter 11 follows Chapter 8, and in this lecture we're going to focus on the structural and physical properties of alcohols versus ethers. We'll also be learning about the nomenclature of ethers and some of the synthetic methods used to access the ether functional group. Here is a breakdown of the videos for this lecture. In video 1 of 3, we will discuss the structure of alcohols and relate this to their different acidities. We will also study the different categories of ether and learn about their nomenclature. In video 2, we will recap some of the physical properties of alcohols versus ethers. There will be a specific focus on solubility and boiling points. In the third and final video, we will discuss the synthetic methods available to synthesize ether functional groups, comparing the usefulness of each method. Alcohols are versatile reagents of organic chemistry, and this is owed to how the carbon-oxygen and oxygen-hydrogen bonds are polarized. The map of electrostatic potential shows that within the alcohol there is an acidic proton, and this is capable of being deprotonated by a stronger base. Alcohols also contain a nucleophilic site, and these are the lone pairs on the oxygen atom. So this means that oxygen of an alcohol can behave as a Lewis base, but it also means that they can behave as a Bronsted base and be protonated too. We saw this in chapters 7 and 8 when studying substitution and elimination reactions. Finally, there is the possibility that once protonated, the electrophilic carbon of an alcohol can also be attacked. In terms of relative acidity of the series provided, alcohols and water are the strongest acids in this series, but they are also the weakest bases. The structure of an alcohol determines the range of pKa's that an alcohol substrate can have, and these we will look at on the next slide. When we're dealing with sp3 hybridized carbon atoms of alcohols, the number of alkyl groups represented by R surrounding the sp3 hybridized carbon atom is what causes the strength of the conjugate base to increase, and hence we see an increase in the pKa values of this particular series. So the alcohols, when deprotonated in this series, they will all have the negative charge localized on the oxygen atom. When such a deprotonation happens, the alkyl groups will push their electron density onto the oxygen atoms. The more alkyl groups there are surrounding the carbon, the more this destabilizes the conjugate base via the inductive effect. However, when the alcohol group is bonded to an sp2 carbon, the pKa values can be up to 10 to the 5 times more acidic, as long as there is the possibility of some resonance stabilization. Let's see this now. The allylic and benzylic alcohols seen in this series are of a similar magnitude in terms of their pKa values. But remember, these alcohols are still bonded to sp3 hybridized carbons, and there is no possibility of resonance stabilization, no matter how tempting it is to try and push any arrows here. However, phenol is 10 to the 5 times more acidic than benzyl alcohol. Well, why is this the case? Take a moment to pause the video and think about this. The slide will advance after 5 seconds to give the answer. Here we see that the negative charge is now placed on an oxygen atom, and this oxygen atom is connected to an sp2 hybridized center, that is the benzene ring. This means that the negative charge can be delocalized over that entire benzene ring, as shown by these resonance structures here. The extra stabilization that is provided by these resonance structures makes phenol considerably more acidic, as the conjugate base is much weaker than the alcohol seen on the previous slide. Now we're going to have a look at ethers and talk about how we categorize these. Ethers contain an oxygen atom that is bridged between two carbon atoms. If we add a mirror plane to the oxygen atom, then there are two possible categories of ether. The first of which is a symmetrical ether. These have R groups that are the same as the R' group, for example, diethyl ether. And this is the name of that symmetrical ether seen on the left. Unsymmetrical ethers arise when the R group is not the same as the R prime group attached to the other side. We can name ethers by naming these alkyl groups alphabetically and then adding the suffix ether. So the ether on the right hand side is known as ethyl propyl ether. These are the common names and they are perfectly acceptable to use on this course. However, I will make you aware that for more complicated ethers, that IUPAC substitutive naming is an option, and we'll look at this on the next slide. More complicated ethers may arise from branched ethers, or having more than one ether functional group in the same molecule. Here it is better to use the IUPAC substitutive naming method. The ether is named as an alkoxy-alkane. In order to deal with ethers that are branched, we can indicate where the branch is using the locant. This is given the appropriate alkoxy prefix. In the case of the first molecule, this is a methoxy group which happens to be on the second carbon of the parent chain. The parent chain contains 5 carbons, therefore the whole name for this ether would be 2-methoxypentane using the IUPAC substitutive naming method. It's also easier when there are multiple ethers in the same molecule to name the alkoxy groups and then add the suffix alkane. Therefore, in the second example, this would be called 1,2-dimethoxyethane. The last type of ether that we will consider are called cyclic ethers, and these are seen on the next slide. IUPAC naming for cyclic ethers may seem a little strange. My recommendation is to use the oxa prefix, as this is common to all of the examples shown on this slide and will allow you to name cyclic ethers with more than one ether functional group. I've included some of the common names here too. A 3-membered cyclic ether, also known as an epoxide, is called oxacyclopropane. This has the alternative name oxarane or the common name ethylene oxide. A 4-membered cyclic ether is named as oxacyclobutane, but this is also known as an oxetane. A 5-membered cyclic ether is known as an oxacyclopentane. This has the common name tetrahydrofuran and is a common aprotic solvent used to solubilize organic compounds. Lastly, when there is more than one cyclic ether group, as in the case of 1,4-dioxacyclohexane, then hopefully you can see why it is better to use the oxa prefix, as this has worked in all of these examples. The last compound can also be called 1,4-dioxane.
This concludes part A.
And in this video we're going to look at some physical properties, namely those of alcohols and ethers, and in particular the boiling points and solubilities of these compounds. So with respect to non-branched alcohols, the boiling points increases as the carbon chain increases. This in turn increases the surface area, which means then that in addition to the hydrogen bonds, there will be an increase in the dispersion forces between these alkyl chains. And this is going to increase the size of temporary dipoles that are set up, and that is why the boiling points increase as the number of carbon atoms in the chains increase. With respect to the solubility of these straight chain alcohols in water, the first 3 alcohols of this homologous series are entirely miscible. After 4 carbons, the solubility or miscibility of the alcohols drops off. And in order to mix a small carbon chain alcohol with water, all of the hydrogen bonds between the water molecules and the hydrogen bonds between the alcohol molecules need to be broken. So energy is required to achieve this. But fortunately, when the small carbon chain alcohol and water are mixed, new hydrogen bonds are made between water molecules and the alcohol molecules. And the energy released when these new hydrogen bonds are made more or less compensates that needed to break the original ones. And in addition, there is an increase in the disorder of the system, that is, an increase in entropy. And this is another factor in deciding whether the solubility occurs or not. Next, when we look at this table, we're going to consider the branched alcohols. So these have two effects on physical properties. In terms of boiling points, an increase in the amount of branching reduces the surface area of the alcohol, and this in turn reduces the dispersion forces, thus lowering the boiling point seen here. However, for the series of branched alcohols containing 4 carbons as highlighted, the increase in branching allows a solvent cage to be formed around the alcohol, and this increases their solubility in water. Lastly, it should come as no surprise that the increase in the number of alcohol groups increases the number of hydrogen bonds and is responsible for the general increase in boiling points. Also, the additional number of hydrogen bonding sites naturally make these diols and triols completely soluble with water. Let's look at some of these intermolecular forces in more detail now. As previously discussed, in terms of boiling points, the alcohol is capable of forming hydrogen bonds as shown. While this intermolecular force is strong, one must not forget about the dispersion forces that increase when the alkyl chain is increased. The increase in molecular weight and the surface area allow for many more temporary dipoles to be formed, and thus increases the boiling point because the amount of energy required to break apart these forces increase. Let's now take a look at the same intermolecular forces in terms of solubility in water. By increasing the chain length of the carbon chain, the effectiveness of the hydrogen bonds to form a solvent cage around the alcohol rapidly falls off after 4 carbons. Let's now introduce the ethers into this discussion. In terms of solubility, let's have a look at these 2 constitutional isomers, that is ethanol and the ether dimethyl ether. Ethanol is entirely miscible with water. Water can easily solvate ethanol as the alkyl portion is particularly small. Also, let's not forget that ethanol and water both contain hydrogen bond donor and acceptor atoms, which aids the formation of the solvent cage. Dimethyl ether, however, only contains a hydrogen bond acceptor atom and can form only one hydrogen bond with water. This is more of a dipole-dipole interaction, seeing as dimethyl ether lacks any hydrogen bond donors. Dimethyl ether is still fairly soluble in water, but relative to ethanol, it is less soluble. With respect to boiling points, when we compare the boiling points of these ethers to alcohols of the same molecular weight, these will always have a lower boiling point. The boiling points of the ethers are more akin to alkanes of a similar molecular weight. The boiling points of cyclic ethers, however, will increase as these have a greater surface area and form more dispersion forces as the size of the ring increases. 1,4-dioxane has the highest boiling point in this series owing to the increase in dipole-dipole interactions between ether groups of these molecules. Let's have another look at those 2 constitutional isomers, that's ethanol and dimethyl ether. So again, we see the importance of hydrogen bonds, though do not forget that both molecules also have dispersion forces and dipole-dipole interactions. Hydrogen bonds are stronger than the dipole-dipole interactions, and this is made very evident by the extreme differences in boiling points between ethanol, which is capable of hydrogen bonding, and dimethyl ether, which does not have hydrogen bonds and only contains the weaker dipole-dipole interactions instead.
This concludes part B.
In this video, we're going to discuss the 2 main methods for the synthesis of ethers. These include the dehydration of alcohols and yield symmetrical ethers with no branching. The other type of ether synthesis allows the synthesis of both symmetrical and unsymmetrical ethers. Let's now take a look at the versatility of the dehydration method first. So intermolecular dehydration reactions require the use of an unbranched primary alcohol. In this case, we have ethanol. When ethanol is reacted together under acidic conditions, typically catalytic sulfuric acid is used at a reduced temperature. Well, this is 140 degrees Celsius, so it's still quite high, then this will afford the diethyl ether product. We'll see the mechanism for this on the next slide. Now, if a higher temperature is used, for example 180 degrees Celsius, this could cause unwanted elimination reactions to occur. So it is worth noting that the alcohol should be an unbranched primary alcohol. If the same reaction is attempted with a secondary or tertiary alcohol, the outcome is more likely to favour an E1 product. Also, if you try to do this with two different primary alcohols to achieve an unsymmetrical ether, this isn't going to work, and you'll just end up with a mixture of ether products, which we'll see later on. Let's now take a look at the mechanism of the intermolecular dehydration route to diethyl ether. In the first instance, the alcohol is protonated by the acid. This turns the alcohol group into a good leaving group, and in the second step of the reaction, ethanol behaves as a nucleophile in an SN2 fashion and yields the protonated alcohol. The third step is the deprotonation step, and this is the final step and can be achieved either by water or by the hydrogen sulfate anion to yield the ether product. Let's see what happens when two different alcohols are used and why this is not a good idea. As you've already heard me allude to in a previous slide on this video, there's going to be no way of controlling which alcohol becomes protonated and then which one is going to behave as the nucleophile. And so if you take these two alcohols and try to react them together to form an unsymmetrical ether, this isn't going to work, and you're just going to end up with a mixture of ethers. So please note the dipropyl ether is also possible, but I forgot to include it. So this is not a synthetically useful method, as this would mean more time in the lab separating out the reaction mixture, aka mess, that has been synthesized. Therefore, it's better altogether to use a different synthetic method. Cue the Williamson ether synthesis, and cue my bad Scottish accent. Meet Alexander William Williamson. This Scottish chemist knew how to make unsymmetrical and symmetrical ethers, but you had to play by his rules. So, how does this work? Well, a general overview is that it's possible to choose the alcohol that is going to behave as a nucleophile and have the alkyl substrate as part of an electrophilic alkyl halide. This is nothing more than an SN2 reaction. So when we think about the reaction, we would probably want to avoid high temperatures, as these typically favour elimination reactions, and this is especially true of secondary and tertiary alkyl halide substrates, which are best avoided altogether. We're also going to need a good leaving group. So conversely, low temperatures minimise the chance of elimination. A primary substrate will definitely favour an SN2 reaction, and good leaving groups always help. Let's take a look at the mechanism for this reaction now. On an earlier slide, we saw the unsymmetrical ether, ethyl propyl ether, and this is how it can be made using the Williamson ether synthesis. Please note that it is also possible to make a symmetrical ether via this method. The first reaction is the formation of the propoxide anion using sodium hydride as a base. The formation of hydrogen is useful in this particular case, as this just leaves the reaction as a gas. Once the propoxide anion is formed, then ethyl iodide can be added dropwise, and by SN2 this unsymmetrical ether, that's ethyl propyl ether, is formed, and there are no other side products made.
This concludes part C.